Tonight, we're going to talk about something happening right now that almost nobody is discussing. On April 1st, 2026, 4 astronauts launched toward the Moon on the Artemis 2 mission. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen. The first humans to leave Earth orbit in 53 years. The news covered the launch, showed the rocket lifting off, talked about returning to the Moon. But here's what they didn't tell you. The most dangerous moment of this mission wasn't the launch. It wasn't even the trans-lunar injection burn that sent them out of Earth orbit on April 2nd. The most dangerous moment is happening right now as you're watching this. Because these 4 people are crossing through a threshold that no human has crossed during solar maximum in over half a century. By the end of tonight, you're going to understand why the next 8 days might be the most consequential test of human deep space exploration we've ever conducted. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The Artemis 2 crew launched into something that space agencies don't advertise. An active geomagnetic storm. Not a massive one, but a G1 classification storm caused by a coronal mass ejection from a solar flare that had already caused radio blackouts days earlier. This wasn't a surprise. Mission Control knew the sun was active. They knew a CME was inbound. They launched anyway, because the launch window was closing, and delays are expensive, and the probabilities said it was acceptable. But here's what makes this different from every other space mission you've heard about. The International Space Station orbits at about 250 miles above Earth, still well within the magnetosphere. Earth's magnetic bubble that deflects most charged particles from the sun. Astronauts on the ISS are protected. Not completely, but significantly. They're still inside Earth's shield. The Artemis 2 crew passed through that shield yesterday. They're now in true interplanetary space. Let me explain what that means. Earth's magnetosphere isn't a hard boundary. It's generated by our planet's molten iron core, which acts like a giant dynamo, creating a magnetic field that extends tens of thousands of miles into space. This field deflects the solar wind, a constant stream of charged particles flowing from the sun at about 900,000 miles per hour. Think of it like an invisible force field. Not perfect, but effective. Inside this bubble, radiation levels are manageable. Outside this bubble, you're exposed to the raw environment of interplanetary space. And right now, Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen are outside that bubble. For the first time since December 1972. But here's the part that should make you pause. They're not just outside Earth's protection. They're outside Earth's protection during solar maximum. The sun operates on an 11-year cycle. Solar minimum is when it's quiet, fewer sunspots, fewer flares, less activity. Solar maximum is when it's chaotic, magnetically complex regions appear, flares erupt, coronal mass ejections launch into space. The current solar cycle, cycle 25, reached its maximum in 2024. We're now in the declining phase. But declining doesn't mean safe. The sun doesn't follow a smooth curve. It's erratic, unpredictable, capable of extreme events, even as overall activity trends downward. And as the Artemis 2 crew launched, a specific active region on the sun was being watched very closely. Active region 4405. A magnetically complex sunspot group with what solar physicists call a beta-gamma classification. That technical term means the magnetic field lines are tangled, with opposite polarities twisted together in close proximity. This configuration has high flare potential, and this region had already proven it was active. On March 29, 2026, just days before launch, active region 4405 produced an X 1.4 class solar flare. The X class is the highest category. X flares are the big ones. This particular flare caused radio blackouts and launched a fast-moving coronal mass ejection toward Earth. That CME arrived on April 1st, launch day, producing the G1 geomagnetic storm I mentioned earlier. But here's what's more concerning. As of launch, active region 4405 was still active, still producing flares, and moving toward the center of the solar disk. Why does that matter? Because position matters enormously for Earth-directed events. A flare from the sun's eastern limb, as it rotates into view, sends particles that might graze Earth or miss entirely. A flare from the western limb, rotating out of view, can be magnetically connected to Earth's position in space, channeling particles along field lines directly toward us. But a flare from the center of the disk, that's aimed straight at us. Direct hit. And active region 4405 was moving into that center position. Before we dive deeper into the probabilities, let's understand what the crew actually experienced during their departure from Earth. The trans-lunar injection burn. This is the threshold moment. Not just a technical maneuver, but the point of no return. At 7:49 p.m. Eastern Time on April 2nd, 2026, Orion's main engine fired for 5 minutes and 50 seconds. The spacecraft, named Integrity by the crew, burned approximately 1,000 pounds of fuel. The engine provides up to 6,000 pounds of thrust, enough to accelerate a car from 0 to 60 miles per hour in about 2.7 seconds. But in space, with a spacecraft mass of 58,000 pounds, it's more subtle. A steady, sustained push that changes velocity by 1,274 feet per second. That doesn't sound like much, but it's enough. Enough to break free from Earth's gravitational grip. Enough to send 4 humans on a trajectory that will take them to the moon and back. Enough to cross from protected space into the void. During the burn, the crew was quiet. Commander Reed Wiseman described it later. They just looked at each other, feeling the vibration through the cabin, watching the numbers on the displays, knowing that every second of that burn was carrying them farther from safety. When it ended, Jeremy Hansen spoke to Mission Control. With that successful TLI, the crew is feeling pretty good up here on our way to the moon. And we just wanted to communicate to everyone around the planet who's worked to make Artemis possible, that we firmly felt the power of your perseverance during every second of that burn. Humanity has once again shown what we are capable of. And it's your hopes for the future that carry us now on this journey around the moon. Beautiful words. Hopeful words. But underneath the optimism, the physics is unforgiving. From that moment on, they were in what's called a free return trajectory. The spacecraft's path is now governed by orbital mechanics. Earth's gravity pulling one way, the moon's gravity pulling another. The trajectory is designed so that even if everything fails, even if the engines won't fire again, the spacecraft will swing around the moon and fall back to Earth. Free return. a safety feature built into the mission design. But free return doesn't protect you from radiation. It doesn't shield you from solar particles. It just means that if you survive whatever happens out there, the laws of physics will bring you home. Now, let's talk about the Van Allen belts. Because the crew had to pass through these on their way out, and they'll pass through them again on the way back. The Van Allen radiation belts are zones of intense radiation trapped by Earth's magnetic field. Discovered in 1958 by physicist James Van Allen using data from the Explorer 1 satellite, there are two main belts. The inner belt extends from about 600 miles to about 3,700 miles above Earth's surface, or roughly 1,000 to 6,000 kilometers. It contains high-energy protons, mostly from cosmic rays that have been captured by Earth's magnetic field. The outer belt extends from about 7,400 miles to about 36,000 miles, or roughly 12,000 to 58,000 kilometers. It contains high-energy electrons, mostly from the solar wind. Between the belts is a region called the slot region, where radiation levels are lower. Though lower is relative. It's still a harsh environment. Now, spacecraft passing through the Van Allen belts accumulate radiation dose, but the passage is relatively quick. For Artemis 2, the belts are crossed during the initial ascent and during the final descent. Hours, not days. And the spacecraft provides shielding. So the belt passage contributes to total mission dose, but it's not the dominant factor. The dominant factor is the time spent beyond the belts, in deep space, where there's no trapped radiation from Earth's magnetic field, but there's no protection either. Just the continuous background from galactic cosmic rays and the possibility of solar particle events. The Artemis 2 trajectory takes the crew to a maximum distance from Earth of approximately 252,021 miles, or 405,600 kilometers. This will break the previous record held by Apollo 13, which reached 248,655 miles, or 400,190 kilometers. Apollo 13, you might remember, was the mission that didn't land. The service module oxygen tank exploded on the way to the moon. The crew had to loop around the moon using the lunar module as a lifeboat and return to Earth. They survived, but it was close. And their distance record has stood for 56 years. Artemis 2 will surpass it by about 3,366 miles. A new record for human distance from Earth. A record that will probably stand until Artemis 3, when a crew will actually land on the lunar surface and spend days there. But records aren't the point. The point is exposure time. Every hour beyond Earth's magnetosphere is another hour of radiation exposure. Every day is another day that the sun might erupt. And the crew is out there for 10 days total. Now, let's talk about probabilities. Space weather forecasters estimated a 75% chance of C-class flares per day from active region 4405. C-class flares are relatively minor. They produce some X-ray emissions, might cause brief radio disturbances, but they don't accelerate particles to dangerous energies. They estimated a 40% chance of M-class flares. M-class flares are moderate. They can cause brief radio blackouts on the sunlit side of Earth. They can produce minor solar particle events, but usually not dangerous ones. And they estimated a 10% chance of X-class flares. X-class flares are the ones that matter for deep space missions. X-class flares produce intense bursts of X-rays. They can cause hour-long radio blackouts, and they can accelerate protons to energies high enough to penetrate spacecraft shielding and cause biological damage. 10% per day doesn't sound like much. But the Artemis II crew isn't in space for one day. They're in space for 10 days. And probability accumulates. If you have a 10% chance of something happening each day for 8 days, the cumulative probability of at least one occurrence is about 57%. Flip a coin 8 times, you'll probably get heads at least once. Same principle. So, as the Artemis II crew crossed out of Earth's magnetosphere on April 2nd, they were entering an 8-day window with better than even odds of experiencing at least one X-class solar flare from a magnetically complex active region aimed roughly in Earth's direction. And there were other active regions too. Region 4409, Region 4404, both contributing to elevated background activity. Plus, a coronal hole high-speed stream forecast to arrive on April 2nd. Coronal holes are areas where the sun's magnetic field opens up, allowing solar wind to escape at higher than normal velocities. When these high-speed streams interact with Earth's magnetosphere, they can trigger geomagnetic storms. Multiple drivers, stacked disturbances, all converging on the exact days the crew is most vulnerable. Crossing the Van Allen belts, transitioning to deep space, exposed for 8 continuous days. Now, you might be thinking, NASA knows all this. They have models, forecasts, contingency plans. They wouldn't launch if it was genuinely dangerous. And you'd be partly right. NASA does know all this. But here's what you need to understand about deep space radiation. There are 2 types of radiation astronauts face: galactic cosmic rays and solar particle events. Galactic cosmic rays are continuous. They come from all directions, all the time. They're high-energy particles, mostly protons and heavy ions, created by supernovae and other violent events across the galaxy. They travel through space for millions of years before reaching our solar system. And they're nearly impossible to shield against effectively. Let me explain why. Galactic cosmic rays are relativistic. That means they're traveling at speeds close to the speed of light. When a proton or heavy ion is moving that fast, it carries enormous kinetic energy. And when something with that much energy hits matter, it doesn't just bounce off. It plows through, creating a cascade of secondary particles as it goes. Imagine shooting a bullet through a wooden board. Now imagine that bullet is moving so fast that instead of stopping in the wood, it punches through and creates splinters that shoot out the other side. That's approximately what happens when a cosmic ray hits shielding material. The primary particle might stop, but it creates neutrons, gamma rays, and other secondary particles that keep going. In some cases, adding more shielding actually makes things worse because you're creating more secondaries. It's called the build-up effect. To block cosmic rays completely, you'd need shielding measured in meters of solid material. Concrete, water, lead, anything dense. But every meter of shielding adds tons of mass. And in space, mass is everything. More mass means more propellant to launch. More propellant means a bigger rocket. A bigger rocket means more cost. Eventually, you reach a point where the mission becomes unfeasible. So spacecraft designers accept that cosmic ray shielding will be imperfect. They minimize it where they can. They use hydrogen-rich materials, like polyethylene, which are better than aluminum at stopping protons. They place critical equipment and crew areas behind as much structural mass as possible. But they know that some radiation will always get through. The dose rate from galactic cosmic rays in deep space is roughly 100 microsieverts per day. For comparison, a chest X-ray is about 20 microsieverts. So one day in deep space gives you roughly the radiation dose of 5 chest X-rays. Over a 10-day mission like Artemis 2, that's about 1 millisievert total from cosmic rays alone. Not negligible, but not immediately dangerous. You'd need to spend months in deep space for cosmic rays to become a significant health concern. And that's the steady state. The background. The thing you can predict and plan for. Solar particle events are different. Solar particle events are bursts. They happen when the sun releases a massive cloud of charged particles, mostly protons, accelerated to enormous energies by the magnetic shock of a flare or coronal mass ejection. These events are not continuous. They're sporadic, intense, and can deliver doses in hours that would normally accumulate over weeks or months. Here's how a solar particle event works. Deep in the sun's atmosphere, magnetic field lines get twisted and tangled by the churning plasma. Regions of opposite magnetic polarity push together. Magnetic energy builds up, and eventually, something gives. The field lines reconnect explosively, a process called magnetic reconnection. This releases enormous amounts of energy in seconds. A large solar flare can release energy equivalent to millions of nuclear weapons. Most of that energy goes into heating the plasma, but some of it accelerates particles. Protons and electrons get caught in the magnetic shockwave and flung outward at a significant fraction of the speed of light. These particles spiral along magnetic field lines, and if the field lines happen to connect to Earth's position in space, the particles follow those lines like railroad tracks, streaming toward us. The highest energy particles arrive first. They're the most dangerous because they penetrate deepest into shielding and tissue. Lower energy particles arrive later, still harmful, but easier to stop with shielding. The particle flux rises rapidly, peaks within an hour or two, and then decays over hours to days. The total dose you receive depends on several factors. The intensity of the initial flare, the efficiency of particle acceleration, your position in space relative to the source, the thickness and composition of your shielding, and the duration of the event. For a minor solar particle event, the dose might be negligible, barely above the cosmic ray background. For a moderate event, you might receive a few millisieverts, enough to increase long-term cancer risk, slightly, but not immediately dangerous. For a major event, like August 1972, the dose can be measured in hundreds of rem, enough to cause acute radiation sickness. And, for an extreme event, a once-in-a-century or once-in-a-millennium storm, the dose could be lethal, even inside a spacecraft. Now, the question becomes, how likely is an extreme event? We have good statistics for small to moderate solar particle events. They happen regularly, multiple times per solar cycle. We can measure them, model them, predict their frequency. But extreme events are rare. By definition, the August 1972 event is one of only a handful of storms of that magnitude in the satellite era. We've only been measuring space weather directly for about 60 years. That's less than 6 solar cycles, which means our sample size for extreme events is very small. Maybe 5 or 10 events that would qualify as dangerous to astronauts. Out of thousands of solar cycles over the Sun's 4.6 billion year history, we've observed a tiny fraction. So when we try to estimate the probability of an extreme solar particle event during a 10-day mission, we're extrapolating from limited data. NASA's models suggest the risk of a mission-threatening event during Artemis 2 is low. A few percent at most. But few percent isn't zero. And when the consequence is crew injury or worse, even small probabilities matter. This is the calculus of deep space exploration. You know the risk exists. You know you can't eliminate it. You mitigate where you can. You accept what you can't change. And you go anyway. Because the alternative is not going. And not going means staying confined to one planet forever. And the dose rate varies by orders of magnitude. A minor solar particle event might barely register above background. A major solar particle event can deliver lethal radiation doses to unshielded astronauts. The August 1972 event, which I'll come back to in detail, would have killed Apollo astronauts if they'd been in space. Not might have, would have. That's not speculation. That's the conclusion of multiple NASA studies analyzing the event years later. So when we talk about radiation risk for Artemis 2, we're not talking about the steady, predictable dose from cosmic rays. We're talking about the possibility of a solar particle event. A tail risk event. The kind that sits in the long tail of the probability distribution, unlikely on any given day, but catastrophic if it occurs. And here's the operational challenge. Solar particle events don't give much warning. A solar flare erupts. X-rays from the flare travel at the speed of light. They reach Earth in 8 minutes. That's your warning bell. But X-rays don't cause the radiation damage. The high-energy protons do, and those protons travel slower. The fastest ones arrive about 15 to 30 minutes after the flare. The bulk of the flux peaks within 30 to 60 minutes. So from flare detection to peak radiation, you have about 30 minutes. Maybe 60 if you're lucky. That's the window to respond. 30 minutes to detect the flare, notify mission control, relay the alert to the crew, assess the situation, make decisions, and execute the shelter protocol. 30 minutes. And that assumes you detect the flare at all. Flares on the far side of the Sun, the side facing away from Earth, produce no X-ray warning. The first indication is when particles arrive. Western limb flares, where the Sun's magnetic field connects to Earth, are the most dangerous, but also somewhat predictable because you can see the active region before it rotates out of view. As the mission progresses, different regions rotate into and out of view. The geometry changes daily. What's visible today is invisible tomorrow. What's invisible today might be visible in 3 days. So the crew is flying through a dynamically changing radiation environment where the threat level shifts with the Sun's rotation and their position in space. Now let's talk about August 1972. Because this is the event that haunts every deep space mission planner. This is the nightmare scenario. The reference case for what can go wrong. The summer of 1972 was supposed to be quiet. The Sun was near solar minimum. The quiet phase of its 11-year cycle. Apollo 16 had just returned in April. Apollo 17 wasn't scheduled until December. NASA was in the gap between missions. Relaxed. On July 29th, an average-sized sunspot group rotated into view over the Sun's eastern limb. McMath region, 11,976. Not particularly large. Not unusually threatening. But magnetically complex. The field lines were tangled, twisted, with steep gradients and opposite polarities pressed close together. A stressed configuration. Unstable. On August 2nd, the region exploded. A series of solar flares erupted over the following days. Not just one or two. A barrage. The largest occurred on August 4th. An enormous X-class flare that launched one of the most powerful coronal mass ejections ever recorded. The CME tore through the Sun's corona and blasted into interplanetary space. But something unusual happened. The preceding flares had already cleared the path, like a snowplow pushing snow off a highway. The earlier CMEs had swept the solar wind aside, creating a low-density channel through the interplanetary medium. So when the August 4th CME launched, it encountered almost no resistance. It accelerated to extraordinary speed, about 6,370,000 miles per hour, or 1,770 miles per second. Nearly 3,000 kilometers per second, racing across 93 million miles of space. It reached Earth in 14.6 hours. The fastest coronal mass ejection transit time ever recorded, before or since. Normal transit time is 2 to 3 days. This one made it in less than a day. And when it arrived, it brought hell with it. The solar energetic particle flux was immense. Protons accelerated to relativistic speeds, spiraling along magnetic field lines, flooding the inner solar system. The intensity peaked at levels rarely seen. Ground-level event, meaning the particle flux was so intense that secondary particles reached Earth's surface despite the protection of the atmosphere. Neutron monitors at high-altitude stations registered enormous spikes. The Forbush decrease, the drop in cosmic ray flux that normally occurs when a CME passes, actually reversed partway through the event because the solar particle intensity was so high. Satellites in orbit experienced malfunctions. Communication systems failed. Power grids on Earth fluctuated. And in Vietnam, something bizarre happened. 4,000 U.S. naval mines spontaneously detonated in Haiphong Harbor. Magnetic influence mines, designed to detect the magnetic signature of ships passing overhead and explode. But the geomagnetic storm from the August 4th CME created magnetic disturbances intense enough to trigger them, all at once, within about 30 seconds. The explosions caused confusion and alarm on both sides of the conflict. Was it an attack? A malfunction? Sabotage? It took weeks to figure out that the sun had done it. Not enemy action, just space weather. This event fundamentally changed how the US military thought about space weather. Within months, the Navy fast-tracked replacement of magnetic-only mines with combined magnetoseismic designs less vulnerable to geomagnetic storms. The Air Force Global Weather Central implemented an automated proton event detection and warning system. The Defense Meteorological Satellite Program, which had been classified, was partially declassified to encourage scientists to study space weather. And NASA, very quietly, held a workshop on space radiation in late October 1972. right before Apollo 17 launched, the last Apollo mission to the moon, because they needed to understand what had just happened, what the crew would have faced if they'd been in space during the August storm. The answer was sobering. Multiple studies analyzed the radiation environment during the event. Data from satellites, ground stations, particle detectors. All of it was fed into models of spacecraft shielding and human radiation exposure. The conclusion was consistent across studies. An astronaut outside a spacecraft in just a spacesuit would have absorbed about 400 rem. That's a massive dose. For comparison, a dose of about 300 to 400 rem has a 50% lethality rate within 30 days if untreated, meaning half the people who receive that dose will die within a month. The other half will be severely ill. 400 rem is right at that threshold. Inside an Apollo command module, the aluminum hull provides some shielding, not a lot. Apollo was built light to save mass, but enough to attenuate the lower energy portion of the particle spectrum. Studies estimated that inside the command module, the dose rate would have peaked at about 66 rem per hour. 66 rem per hour. For a multi-day solar particle event. The peak lasted for hours. The elevated flux continued for days. You mitigate where you can. You accept what you can't change. And you go anyway. Because the alternative is not going. And not going means staying confined to one planet forever. And the dose rate varies by orders of magnitude. A minor solar particle event might barely register above background. A major solar particle event can deliver lethal radiation doses to unshielded astronauts. The August 1972 event, which I'll come back to in detail, would have killed Apollo astronauts if they'd been in space. Not might have. Would have. That's not speculation. That's the conclusion of multiple NASA studies analyzing the event years later. So when we talk about radiation risk for Artemis 2, we're not talking about the steady, predictable dose from cosmic rays. We're talking about the possibility of a solar particle event. A tail risk event. The kind that sits in the long tail of the probability distribution, unlikely on any given day, but catastrophic if it occurs. And here's the operational challenge. Solar particle events don't give much warning. A solar flare erupts. X-rays from the flare travel at the speed of light. They reach Earth in 8 minutes. That's your warning bell. But X-rays don't cause the radiation damage. The high-energy protons do. And those protons travel slower. The fastest ones arrive about 15 to 30 minutes after the flare. The bulk of the flux peaks within 30 to 60 minutes. So, from flare detection to peak radiation, you have about 30 minutes. Maybe 60 if you're lucky. That's the window to respond. 30 minutes to detect the flare, notify mission control, relay the alert to the crew, assess the situation, make decisions, and execute the shelter protocol. 30 minutes. And that assumes you detect the flare at all. Flares on the far side of the Sun, the side facing away from Earth, produce no X-ray warning. The first indication is when particles arrive. Western limb flares, where the Sun's magnetic field connects to Earth, are the most dangerous, but also somewhat predictable, because you can see the active region before it rotates out of view. As the mission progresses, different regions rotate into and out of view. The geometry changes daily. What's visible today is invisible tomorrow. What's invisible today might be visible in 3 days. So the crew is flying through a dynamically changing radiation environment where the threat level shifts with the sun's rotation and their position in space. Now, let's talk about August 1972, because this is the event that haunts every deep space mission planner. This is the nightmare scenario, the reference case for what can go wrong. The summer of 1972 was supposed to be quiet. The sun was near solar minimum, the quiet phase of its 11-year cycle. Apollo 16 had just returned in April. Apollo 17 wasn't scheduled until December. NASA was in the gap between missions, relaxed. On July 29th, an average-sized sunspot group rotated into view over the sun's eastern limb, McMath region 11,976. Not particularly large, not unusually threatening, but magnetically complex. The field lines were tangled, twisted, with steep gradients and opposite polarities pressed close together. A stressed configuration, unstable. On August 2nd, the region exploded. A series of solar flares erupted over the following days. Not just one or two, a barrage. The largest occurred on August 4th, an enormous X-class flare that launched one of the most powerful coronal mass ejections ever recorded. The CME tore through the sun's corona and blasted into interplanetary space. But something unusual happened. The preceding flares had already cleared the path, like a snowplow pushing snow off a highway. The earlier CMEs had swept the solar wind aside, creating a low-density channel through the interplanetary medium. So when the August 4th CME launched, it encountered almost no resistance. It accelerated to extraordinary speed, about 6,370,000 miles per hour, or 1,770 miles per second, nearly 3,000 kilometers per second, racing across 93 million miles of space. It reached Earth in 14.6 hours, the fastest coronal mass ejection transit time ever recorded, before or since. Normal transit time is 2 to 3 days. This one made it in less than a day. And when it arrived, it brought hell with it. The solar energetic particle flux was immense. Protons accelerated to relativistic speeds, spiraling along magnetic field lines, flooding the inner solar system. The intensity peaked at levels rarely seen. Ground-level event, meaning the particle flux was so intense that secondary particles reached Earth's surface despite the protection of the atmosphere. Neutron monitors at high-altitude stations registered enormous spikes. The Forbush decrease, the drop in cosmic ray flux that normally occurs when a CME passes, actually reversed partway through the event because the solar particle intensity was so high. Satellites in orbit experienced malfunctions. Communication systems failed. Power grids on Earth fluctuated. And in Vietnam, something bizarre happened. 4,000 U.S. naval mines spontaneously detonated in Haiphong Harbor. Magnetic influence mines, designed to detect the magnetic signature of ships passing overhead and explode. But the geomagnetic storm from the August 4th CME created magnetic disturbances intense enough to trigger them, all at once, within about 30 seconds. The explosions caused confusion and alarm on both sides of the conflict. Was it an attack? A malfunction? Sabotage? It took weeks to figure out that the sun had done it. Not enemy action, just space weather. This event fundamentally changed how the US military thought about space weather. Within months, the Navy fast-tracked replacement of magnetic-only mines with combined magnetoseismic designs less vulnerable to geomagnetic storms. The Air Force Global Weather Central implemented an automated proton event detection and warning system. The Defense Meteorological Satellite Program, which had been classified, was partially declassified to encourage scientists to study space weather. And NASA, very quietly, held a workshop on space radiation in late October 1972, right before Apollo 17 launched, the last Apollo mission to the Moon, because they needed to understand what had just happened, what the crew would have faced if they'd been in space during the August storm. The answer was sobering. Multiple studies analyzed the radiation environment during the event. Data from satellites, ground stations, particle detectors. All of it was fed into models of spacecraft shielding and human radiation exposure. The conclusion was consistent across studies. An astronaut outside a spacecraft, in just a spacesuit, would have absorbed about 400 rem. That's a massive dose. For comparison, a dose of about 300 to 400 rem has a 50% lethality rate within 30 days if untreated, meaning half the people who receive that dose will die within a month. The other half will be severely ill. 400 rem is right at that threshold. Inside an Apollo command module, the aluminum hull provides some shielding. Not a lot. Apollo was built light to save mass, but enough to attenuate the lower energy portion of the particle spectrum. Studies estimated that inside the command module, the dose rate would have peaked at about 66 rem per hour. 66 rem per hour for a multi-day solar particle event. The peak lasted for hours. The elevated flux continued for days. Over the course of a typical lunar mission, 11 to 14 days, an Apollo crew would have accumulated a cumulative skin dose of about 358 rem. 358 rem. Well into the range of acute radiation sickness. What does that mean in practice? Radiation sickness occurs when exposure damages rapidly dividing cells. The lining of the intestines, bone marrow, where blood cells are produced, cells in hair follicles. At doses around 100 to 200 rem, you start seeing symptoms. Nausea, fatigue, temporary decrease in white blood cells. At 200 to 400 rem, the symptoms get worse. Severe nausea and vomiting within hours. Diarrhea, dehydration, significant drop in white blood cells, increasing infection risk. Hair loss, skin reddening and burns on exposed areas. At 358 rem, you're looking at severe acute radiation syndrome. The crew would have been incapacitated within days, unable to perform their duties, unable to navigate the spacecraft, possibly unconscious. NASA's best projections, based on radiation medicine knowledge available in 1972, suggested that crew members would have required immediate hospitalization upon return. 3 to 6 months of intensive care. Blood transfusions to replace damaged bone marrow. Antibiotics to fight infections their compromised immune systems couldn't handle. Fluid replacement for dehydration. Pain management. Treatment for burns. And even with all that care, there was a 20% chance they wouldn't survive. 20%. 1 in 5. Those aren't odds you want to face. But here's the terrifying part. It was pure luck. Complete chance. Random timing. Apollo 16 returned on April 27, 1972. The August storm hit on August 2nd through 11th. Apollo 17 launched on December 7th. If Apollo 16 had been delayed by 3 months for any reason, technical issues, weather, anything, the crew would have been in space during the storm. If Apollo 17 had been moved up by 4 months, same thing. It almost happened. The gaps between Apollo missions were not planned around solar activity. NASA didn't have the forecasting capability to predict storms months in advance. They just launched when the hardware was ready and the weather was acceptable. And in this case, that meant they got lucky. Incredibly lucky. The difference between a successful mission and a potential disaster was measured in weeks. That event is seared into NASA's institutional memory. Every deep space mission plan since 1972 has referenced August 1972 as the baseline, worst case. Radiation shielding requirements are designed to handle August 1972 level events. Crew exposure limits are set with August 1972 in mind. Space weather forecasting investment was driven partly by the recognition that we can't rely on luck. And yet, here we are, 53 years later, launching the Artemis II crew during a solar cycle that, while less active than some, is still capable of producing extreme events, and hoping that history doesn't repeat itself. Because, if an August 1972 scale event occurs during the next 8 days, we're going to find out whether our modern technology and planning are actually better than Apollo, or whether we've just been lucky for 53 years. There's a detail about August 1972 that doesn't get enough attention. The warning time was essentially 0. In 1972, space weather monitoring was primitive. A few satellites with particle detectors. Ground-based solar observations. No real-time forecasting capability. The first indication that something was wrong came when the particles arrived. Satellite operators noticed anomalies. Communications degraded. Ground stations saw the geomagnetic disturbances, but there was no advance warning. No 8-minute X-ray alert. No model predicting CME arrival time. The event just happened, and everyone scrambled to respond. Today, we're better. We have satellites like the Solar Dynamics Observatory, constantly watching the sun in multiple wavelengths. We have GOES satellites, monitoring X-ray flux in real time. We have ACE and DISCOVER at the L1 point providing upstream solar wind measurements. We have models that can predict CME arrival time within a few hours based on initial velocity and direction. We have dedicated space weather forecasters at NOAA working 24/7. So, we should get warning. Should. But should isn't will. ACE is 28 years old, way past its design life. It's held together by redundant systems and careful management. If it fails, and it could fail at any time, we lose critical upstream monitoring. DISCOVER is newer, launched in 2015, but it's a single point of failure. One spacecraft at L. One doing a job that probably should have 3 or 4 redundant platforms. Budget constraints. Priorities. We make do with what we have. And solar physics is hard. Really hard. We can see sunspots. We can measure magnetic field configurations. We can detect when a flare erupts. But predicting exactly when a flare will occur, how large it will be, what direction the CME will go, how fast it will travel, and what the particle energy spectrum will look like is still beyond our capability. We can give probabilities. 10% chance of an X-class flare today. 40% chance of an M-class flare. But we can't say with certainty that a specific active region will or won't erupt in the next hour. And we especially can't predict far-side events. Active regions on the far side of the Sun, currently facing away from Earth, are invisible to most of our monitoring systems. We have some capability to detect them using helioseismology, analyzing oscillations in the Sun's surface that reveal magnetic regions on the far side. But it's limited, low, resolution, uncertain. A major active region could be developing on the far side right now, ready to rotate into view in a week, and we wouldn't know it's dangerous until it actually appears. By which time, the Artemis 2 crew might be approaching the Moon. 200,000 miles from Earth. Days from home. This is the environment they're operating in. Not perfect knowledge. Not complete safety, but calculated risk based on the best information available, and a recognition that some risks can't be eliminated, only accepted. Let's talk about what the crew is experiencing right now. Right this minute, on April 3rd, 2026. Flight Day 3 of the mission. They're approximately 230,000 miles from Earth, or 370,000 kilometers. Moving away at roughly 2,000 miles per hour, or 3,200 kilometers per hour. Not under power. The trans-lunar injection burn ended yesterday. Now they're coasting, following the free return trajectory. Pulled by Earth's gravity, pulled by the Moon's gravity, following the orbital mechanics that Newton figured out 300 years ago. Inside Orion, the environment is carefully controlled. Temperature maintained at about 70 degrees Fahrenheit or 21 degrees Celsius. Comfortable. Humidity regulated to prevent condensation. Oxygen, partial pressure, kept at levels that support life without being wasteful. Carbon dioxide scrubbed from the air by chemical canisters. The life support system works quietly in the background. Fans moving air. Pumps circulating coolant. Sensors monitoring everything. All of it automated. All of it critical. If any major system fails, the mission becomes very complicated very quickly. The crew can hear the spacecraft. It's not silent. There's the hum of the fans, the occasional click of a valve, the creak of structure as thermal expansion and contraction shift the aluminum panels. In microgravity, sound travels differently. No convection to carry it. It propagates through the structure itself, so you hear things directly through the hull. Vibrations, subtle movements. After a few days, you learn to interpret them. That click means the attitude control thrusters fired. That hum means the life support fans cycled. That creak is just thermal stress, nothing to worry about. But every unfamiliar sound gets your attention. Because in space, unexpected noises can mean problems. And problems in space can cascade quickly. The crew is busy. Despite what movies show, spaceflight is not mostly floating around looking at Earth. It's work. Constant work. System checks. Experiments. Exercise. Meal preparation. Waste management. Communication with mission control. And right now, photography training. On April 6th, they'll make their closest approach to the moon. 4,000 miles. That's close in cosmic terms. About 2% of the distance from Earth to the moon. But it's not landing. They won't even orbit. Just a flyby. A gravitational slingshot that sends them back toward Earth. During that flyby, they have a packed schedule. Photograph specific lunar features. Document geological formations. Test the spacecraft's cameras and targeting systems. Practice the procedures that Artemis 3 will use when they actually land. And observe the solar eclipse. From Orion's perspective, swinging around the far side, the sun will disappear behind the moon. Total eclipse. But not like an eclipse on Earth. On Earth, during totality, the sky darkens, but you can still see scattered light from the atmosphere. The sun's corona glowing around the moon's edge. In space, there's no atmosphere to scatter light. When the moon blocks the sun, it's dark. Absolutely dark. The crew will see stars that are normally invisible. The Milky Way. The zodiacal light. Maybe, if they're lucky, a comet or two. And they'll look for meteoroid impacts on the lunar surface. Without an atmosphere, meteoroids hit the moon constantly. Small ones, mostly. Pebble-sized. But they hit at tens of thousands of miles per hour. And when they impact, they vaporize. Create a flash of light. A brief plasma plume, usually too faint to see from Earth. But from 4,000 miles away, with the moon in darkness, those flashes should be visible. Documenting them helps scientists understand the meteoroid flux in the Earth-Moon system, helps estimate impact rates, helps plan where future lunar bases should and shouldn't be built. So even the eclipse observation has scientific value. Nothing wasted. Every moment of the mission is planned. But underneath all the scheduled activities, there's the awareness, the radiation environment, the solar activity, the active regions still churning on the sun. The crew receives updates twice a day. Morning briefing from mission control. Space weather summary. Active region status. Flare activity in the past 12 hours. Forecast for the next 12 hours. Radiation dose accumulated so far. And then another briefing in the evening. Same information, updated. The updates are delivered calmly. Matter of fact. No drama. Just data. But the crew knows how to read between the lines. When mission control says active region 4405 remains magnetically complex, they know that means flare risk is still elevated. When they say SWPC maintains a 10% daily probability for X-class flares, they know that probability is accumulating. When they say no significant particle events detected in the past 12 hours, they know that's good, but doesn't guarantee the next 12 hours will be the same. So far, the mission has been nominal. Everything working as planned. No major anomalies. The toilet issue on flight day 1 was minor, resolved within hours. Turned out to be a sensor glitch, not an actual malfunction. The proximity operations demonstration, where the crew manually maneuvered Orion relative to the discarded upper stage, went perfectly. The trans-lunar injection burn was flawless. Engine performance exactly as predicted. Trajectory within acceptable parameters. Every system check has come back green. Nominal. That's the word mission control uses. Nominal means normal, expected, within specifications. It's a boring word. And in spaceflight, boring is good. Boring means nothing's breaking, nothing's on fire. Nobody's panicking. You want boring, but boring can also make you complacent. And complacency in space is dangerous, because the environment doesn't care how well things have gone so far. A solar particle event doesn't wait for you to have problems first. It just happens. And when it happens, you have 30 minutes to respond. Ready or not. The crew understands this. They're professionals. They know the difference between careful vigilance and paranoia. They're not staring at the radiation displays every second, but they're aware. And they've already discussed amongst themselves what they'll do if the alert comes. Who moves where? Who grabs which equipment? Who communicates with mission control? The division of labor. They've talked through scenarios. What if the alert comes while we're sleeping? What if it comes during the lunar flyby when we're busy with photography? What if it comes right before re-entry when we're strapped in and can't move freely? For each scenario, they have a plan. Not formal, not written down as procedures, just crew discussions, making sure everyone knows what everyone else will do. So when the moment comes, if it comes, they can act without confusion, without wasted time. This is how professional crews operate. They anticipate. They prepare. They talk through contingencies. Not because they expect things to go wrong, but because being surprised is how you get killed in space. And they don't want to be surprised. Reed Wiseman, the commander, sets the tone. Calm, methodical, attentive to details. He checks systems even when they're showing green. He asks questions when something seems slightly off, even if it's within tolerances. He encourages the crew to voice concerns, no matter how minor, because small problems become big problems if you ignore them. Victor Glover, the pilot, is the systems expert. He knows Orion inside and out. Every circuit, every valve, every backup system. If something fails, he's the one who'll diagnose it and figure out the workaround. He spent months before the mission in simulators, running failure scenarios. Electrical problems, propulsion malfunctions, life support degradations, every possible thing that could go wrong. So now, in flight, when he sees a parameter trending in an unexpected direction, he recognizes it instantly. And he knows whether it's something to worry about or just normal variation. Christina Koch, mission specialist, is the science lead. She coordinates the experiments, manages the photography schedule, makes sure the data collection is happening correctly. But she's also crew medical officer, trained in emergency medicine. If someone gets sick or injured, she's the one who'll provide care. And if there's a radiation event, she's the one who'll monitor the HERA displays. track the dose rates, estimate the biological exposure, and make the call on whether the shelter is providing adequate protection or whether they need to take additional measures. What additional measures? Not many options. They can't add shielding. They don't have. They can't abort the mission, but they can optimize positioning. Rotate the spacecraft to put maximum mass between the crew and the sun. They can adjust their activity levels. Less exertion means lower metabolic rate, means less oxygen. Consumption means less time outside the shelter. Small things. But when you're accumulating dose, small things matter. And Jeremy Hansen, the Canadian mission specialist, brings fresh eyes. This is his first spaceflight. He doesn't have years of ISS experience to draw on. But that's actually valuable, because he's not jaded. He doesn't assume things will be fine just because they've always been fine before. He asks questions that more experienced astronauts might not think to ask. He notices things that might slip past someone who's seen it all before. And he's also the voice to the public, the communicator. When they do downlinks, when they send messages back to Earth, Hansen often speaks. Articulate, thoughtful, able to convey the significance of what they're experiencing in ways that resonate with people who've never been to space. That's the crew. 4 people, thousands of miles from Earth, doing something that hasn't been done in over 50 years. And doing it during solar conditions that make the risk real. Not theoretical. Real. Let's start with the basic structure. Orion consists of 2 main parts. The crew module, where the astronauts live and work, and the service module, which provides propulsion, power, and life support. The crew module is shaped like an Apollo capsule, but larger, about 16.5 feet in diameter. The walls are made of aluminum alloy with an ablative heat shield on the base. The heat shield is crucial for re-entry, but it also provides some radiation shielding. It's the thickest, densest part of the spacecraft, which is why the shelter protocol positions the crew near it. The service module, built by the European Space Agency, wraps around the crew module's base. It carries solar arrays, propellant tanks, thrusters, and the main engine. All of that equipment and structure adds mass between the crew and incoming radiation from certain directions. Not a lot of mass. Spacecraft are built to be as light as possible while still being functional. But every gram helps. Inside the crew module, the layout is designed for efficiency. 4 seats for launch and re-entry. Storage lockers along the walls containing food, water, equipment, and supplies. Displays and controls for the crew to monitor systems and navigate. Exercise equipment, because even on a 10-day mission, muscle loss in microgravity is a concern. Life support systems that scrub carbon dioxide from the air, provide oxygen, regulate temperature and humidity. Communication systems to stay in contact with mission control, and the HERA radiation sensors. HERA stands for Hybrid Electronic Radiation Assessor. These sensors continuously measure the radiation environment inside the spacecraft. Different detectors for different particle types and energy ranges. The data is displayed to the crew in real time and transmitted to mission control on Earth. So, NASA knows, second by second, what the radiation levels are. This is a huge improvement over Apollo. Apollo had dosimeters, small badges the astronauts wore that would be developed after the mission to see how much radiation they'd received. passive monitoring. You find out afterward. HERA is active monitoring. You know immediately, which means you can respond. If the HERA sensors detect a sudden spike in proton flux, Mission Control can alert the crew instantly. Begin the shelter protocol. The shelter protocol is straightforward in concept, but labor-intensive in execution. When an alert comes, the crew has about 30 minutes before peak particle flux arrives. They need to move to the designated shelter area. This is a section of the crew module positioned near the heat shield, where the structural shielding is already maximum. Then, they start building additional shielding. Pull water containers from storage and stack them around the shelter area. Water is heavy, about 8 pounds per gallon, and hydrogen is excellent at scattering and absorbing protons. Pull food supplies, dense packages that add mass. Pull equipment, anything that can be positioned to create layers between the crew and the incoming radiation. Rearrange the cabin to maximize shielding thickness in the direction of the sun. Once the shelter is configured, the crew stays there, huddled in a small space, surrounded by bags of water and food, monitoring the HERA displays, watching the dose rate climb, waiting for it to peak and decline. They can still perform basic tasks. Eat, drink, use the toilet, which hopefully is still working after that earlier glitch. But they can't move freely around the cabin. They need to stay in the shelter until the event passes. Hours, potentially. Maybe a full day, if it's a long-duration event. It's not comfortable. It's not pleasant. But it's survivable. Probably. The effectiveness of the shelter depends on the energy spectrum of the incoming particles. Lower energy protons are easier to stop. A few centimeters of water or aluminum will attenuate them significantly. Higher energy protons punch through. You need tens of centimeters, even meters, to stop them. And the highest energy particles, the relativistic ones, are almost unstoppable with reasonable amounts of shielding. So the shelter works well for moderate solar particle events where most of the flux is lower energy protons. For an extreme event with a hard spectrum, lots of high energy particles, the shelter helps but might not be enough. This is where uncertainty comes in. We know the shelter reduces dose. We can calculate by roughly how much based on the mass thickness and composition. But the exact effectiveness depends on the exact particle energy distribution, which we won't know until the event is happening. And even then, measurements have uncertainties. The HERA sensors give you flux and energy, but converting that to biological dose requires models of how particles interact with tissue. Models that are validated against laboratory experiments and animal studies, but never tested on actual humans in actual space during an actual extreme solar particle event. So there are error bars, confidence intervals, ranges of possible outcomes. NASA's pre-mission analysis says the shelter should provide adequate protection for all but the most extreme events. Top 1% of the distribution. Storms larger than anything we've seen in the satellite era. For those, the outcome is uncertain. The crew might be okay. They might receive doses high enough to cause radiation sickness. They might, in a worst-case scenario, receive lethal doses. It depends on specifics we can't predict. But the probability of such an extreme event during a 10-day window is estimated at well under 1%, low enough that NASA judged the mission acceptable, high enough that it's not zero. And when you're the one in the spacecraft, the difference between 1% and 0 feels very significant. Orion's electronics must tolerate the radiation environment. This is a separate challenge from protecting the crew. Humans can tolerate certain doses and recover. Electronics can't recover. A bit flip is permanent unless you catch it and correct it. Modern spacecraft use radiation-hardened components. Chips designed to resist single-event upsets. Redundancy. So if one system fails, a backup takes over. Error correction codes in memory. Watchdog timers that reset systems if they hang. All of these techniques make electronics more resilient. But nothing is perfect. A sufficiently intense particle flux can overwhelm even hardened systems. And Orion's computer systems are critical. Navigation, guidance, life support, communications, all dependent on functioning electronics. If a solar particle event causes widespread system failures, the crew could lose the ability to navigate, to communicate with Earth, even to control life support. At that point, they're riding a dead spacecraft on a ballistic trajectory, hoping the free return brings them back close enough to Earth that they can manually orient for re-entry and deploy parachutes. Possible, but extremely risky. This is another reason why solar particle events are taken so seriously. It's not just about crew health. It's about mission success. A spacecraft with fried electronics and a sick crew is in desperate trouble. And rescue is not an option. There's no way to send another spacecraft to intercept them in deep space on short notice. If something goes catastrophically wrong, they're on their own until they get back to Earth. Days away. Mission control on the ground must make correct decisions under pressure with incomplete data. They're watching the same displays the crew sees. They have access to more data, more analysis tools, more experts to consult. But they're also 93 million miles from the Sun and 200,000 miles from the crew. Everything they know comes through sensors and telemetry. Measurements with error bars. Models with assumptions. Forecasts with uncertainties. When an X-class flare erupts, mission control has minutes to decide. Is this a minor event or a major one? Should we wake the crew if they're sleeping? Should we activate the shelter protocol? Can we wait for more data, or do we need to act now? These decisions have consequences. Activate the shelter unnecessarily, and you disrupt the mission timeline. Stress the crew, use resources. Fail to activate when you should, and you put the crew at risk. There's no perfect answer. Just best judgment under pressure. And the people making those calls are human, capable of error, subject to fatigue, stress, cognitive biases. They train for this. They practice. They have checklists and decision trees. But simulations aren't reality. The first time mission control has to make a real solar particle event shelter decision with actual astronauts in actual deep space will be during Artemis 2. If it happens. Every link in this chain has been tested individually. The HERA sensors have been calibrated in particle accelerators. The shelter protocol has been practiced in mock-ups on the ground. The communication systems have been tested. The radiation-hardened electronics have been exposed to laboratory radiation sources. The forecasting models have been validated against historical events. But they've never all been stressed simultaneously under actual extreme solar particle event conditions. Because we haven't had one since humans were last in deep space. December 1972. 53 years ago. So the Artemis 2 mission is, in a very real sense, a test. Not just of the Orion spacecraft, not just of the crew's training, a test of the entire integrated system for managing deep space radiation during solar maximum. The sensors, the protocols, the communications, the decision-making, the shielding, the electronics, all of it, working together under real conditions. And we won't know if the system works until it's tested. Now, there's something else that happened around the Artemis 2 launch that I want to mention. Not because it's directly related, but because the convergence is striking. In the 12-hour window around launch, on April 1st, 2026, Earth experienced unusual activity. A magnitude 7.4 earthquake struck Indonesia. Tsunami warnings were issued, evacuations occurred. The National Weather Service issued 469 alerts across the United States for severe weather. Tornadoes, flash flooding, extreme conditions. And the geomagnetic storm from the March 29th CME was affecting power grids and GPS systems. All of this in a 12-hour window. Now, I need to be very clear here. There is no established scientific mechanism linking G1 geomagnetic storms to earthquake triggering on these timescales. The energy involved in a geomagnetic storm and the energy involved in an earthquake are completely different. Some peer-reviewed studies have found statistical correlations between elevated geomagnetic activity and slightly increased seismic rates over 1 to 3 day windows, looking at population-level statistics. But these are weak correlations, not predictive relationships. The proposed physical mechanisms, like piezoelectric effects in crustal rocks or ionospheric coupling to the lithosphere, are plausible in principle but unproven, at scales relevant to triggering magnitude 7 events. So the earthquake and the storm happening simultaneously was, most likely, coincidence. But here's why I mention it. The contrast. Earth's chaos, the earthquake, the severe weather, the geomagnetic disturbances, all of it occurred within planetary systems. An atmosphere to contain the weather. A magnetosphere to channel and dissipate the solar wind. Emergency services, hospitals, infrastructure, evacuation routes. Billions of years of accumulated survival knowledge encoded in biology and civilization. The Artemis 2 crew is heading into an environment with none of that. No atmosphere, no magnetosphere, no rescue, no hospital. Just 4 people, a spacecraft, and the protocols they've trained on. If something goes wrong, the nearest safe haven is Earth. 250,000 miles away. Days of travel time. They can't evacuate. They can't get medical care. They can only shelter, wait, and hope the shielding holds. That's the nature of deep space. You accept risks that would be unacceptable on Earth because there's no other way to explore. And here's what makes this even more profound. The crew knows all of this. Reed Wiseman, Victor Glover, Christina Koch, Jeremy Hansen. They're not naive. They know the solar physics. They know about August 1972. They know about the 30-minute window. They know about the limitations of the shelter. They know the probabilities. They made an informed choice, with full knowledge of the tail risks. But let's be clear about what informed choice means in this context. It doesn't mean they know exactly what will happen. Nobody knows that. Not them. Not mission control. not the solar physicists monitoring the sun. What it means is they understand the range of possible outcomes. The best case, the worst case, and everything in between. And they've decided that the mission is worth pursuing despite the uncertainty. This is prospective courage, not reactive bravery. Reactive bravery is what happens when crisis strikes, and you respond instinctively. The fighter pilot, whose engine fails, and who stays with the aircraft long enough to steer it away from populated areas before ejecting. The first responder who runs into a burning building to save someone. The astronaut who troubleshoots a critical system failure in real time to save the mission. All of those are brave. All of those are admirable. But their responses to situations that have already developed. Prospective courage is different. It's the decision to walk into known danger before the crisis even occurs. Knowing what might happen. Knowing you might not come back. Going anyway. That's what the Artemis 2 crew has done. They sat in briefings for months. Learning about solar particle events. Learning about August 1972. Learning about radiation sickness. Learning about the probabilities. They understood, intellectually and viscerally, what they were signing up for. And they said yes. Not because they're reckless, not because they don't understand the risks, but because they've weighed the risks against the value of the mission and decided the value is greater. This kind of decision-making requires a certain mindset. You have to be able to think probabilistically. To understand that a 10% daily probability of an X-class flare doesn't mean it won't happen. It means it probably won't happen today, but might. And that the cumulative probability over 8 days is higher. And that even small probabilities become significant when the stakes are high. You have to be able to separate controllable risks from uncontrollable ones. You can control your training. You can control your preparation. You can control how quickly you respond when an alert comes. But you can't control the sun. You can't make active region 4405 go quiet. You can't prevent a solar particle event. You can only prepare to deal with it if it happens. Accepting that distinction, accepting that there are things beyond your control, requires a certain philosophical maturity. And you have to be able to function effectively despite the awareness of danger. Not by ignoring it, not by pretending it doesn't exist, but by acknowledging it and not letting it paralyze you. This is perhaps the hardest part, because human brains are not well designed for this. We evolved to respond to immediate threats. The predator in the bushes. The cliff edge in the darkness. Things that require instant action. We're not well adapted to living with long-term probabilistic threats. The threat that might materialize tomorrow, or the next day, or not at all. It creates a low-level background stress, a constant awareness that something might go wrong. And managing that stress, staying focused on the mission tasks, despite it, requires discipline, mental discipline, emotional regulation, the ability to compartmentalize, to put the fear in a box and close the lid when you need to focus on work. Astronauts are selected partly for this ability. They go through psychological screening, personality assessments, interviews, simulations where they're put under stress to see how they react. The people who make it through tend to share certain traits. Calm, under pressure, able to think clearly when things go wrong, not prone to panic. comfortable with uncertainty, able to make decisions with incomplete information, and, perhaps most importantly, motivated by something beyond self-preservation. Because if your primary motivation is staying alive, deep space exploration is a terrible choice. The risks are real. The dangers are significant. Statistically, you're safer staying on Earth. Much safer. But the people who become astronauts aren't primarily motivated by safety. They're motivated by exploration, by discovery, by contributing to something larger than themselves, by being part of the human story of expansion into the cosmos. And that motivation is strong enough to outweigh the fear. Not eliminate it. Nobody is fearless. Anyone who says they have no fear in situations like this is either lying or dangerously disconnected from reality. The fear is there. It's rational. It's appropriate. But it's not in control. The mission is in control. The purpose is in control. And the fear is just background noise. There's a moment that capsule communicator, Capcom, described from the pre-launch preparations. 3 days before launch. The crew was in quarantine, isolated to prevent any last-minute illness. They were going through final checks, equipment verification, procedure reviews. And Reed Wiseman said something interesting to the team. He said, "We know what we're getting into. We know it's not going to be easy. We know there are risks we can't eliminate. But we also know that every person who worked on this mission, every engineer, every technician, every flight controller, has done everything possible to make this succeed. And we trust that. We trust the hardware. We trust the procedures. We trust the people on the ground. And because of that trust, we can do our job." That statement reveals something important. Deep space exploration is not a solo endeavor. It's not just the crew taking risks. It's thousands of people working together, each person doing their part, each contribution critical. The engineer who designed the radiation shielding, the technician who assembled the HERA sensors, the software developer who wrote the code for the shelter protocol alerts, the flight controller who will monitor telemetry 24/7, the space weather forecaster who tracks active regions and models CME trajectories. All of them are part of the mission. And the crew's ability to accept risk is built on trust in all of those people. Trust that they did their jobs correctly. Trust that the systems work. Trust that if something goes wrong, the ground team will help them solve it. That trust is earned over months and years. Through training, through simulations, through working together on smaller problems and seeing how the team responds. By the time you're strapping into a spacecraft for launch, you've worked with these people for so long that you know their capabilities. You know their judgment. You know they won't let you down. And that knowledge makes it possible to climb into a metal can and let it throw you at the moon. Now, there's an aspect of this that we haven't talked about. The families. The people left behind. These are people with lives, connections, responsibilities. They're not solitary adventurers with nothing to lose. And when they launch into space, especially on a mission with real risks, they're making a choice that affects all of those people. The families know the risks too. They sat through the same briefings, or versions of them. They understand what might happen, and they have to live with that knowledge for the entire mission. Waiting, watching. That's its own kind of courage. The courage to let someone you love do something dangerous because it matters to them, because it's their purpose, because stopping them would diminish who they are. It's a different kind of sacrifice. NASA provides support for families during missions, dedicated liaisons who keep them updated, psychologists available if needed, community among astronaut families who understand what each other is going through. But at the end of the day, the waiting is lonely. You can't truly share it with someone who hasn't experienced it. And during Artemis 2, with the solar activity and the radiation risks, that waiting has an extra edge. The families know about active region 4405. They know about the probabilities. They know that any day the call might come. There's been an event. We're monitoring the situation. We'll keep you updated. And then more waiting. Waiting to find out how severe it is. Waiting to hear that the crew is okay. This is the human cost of exploration, not just the risk to the explorers themselves, but the burden on everyone who loves them. It's easy to romanticize space exploration, to focus on the heroism and the achievement and the expansion of human knowledge. All of that is real. But so is the cost, the stress, the separation, the risk of loss. And it's important to acknowledge that cost, because it's part of the calculation. Is expanding human presence in the solar system worth the risk to individual lives? Is it worth the burden on families? Is it worth the resources we invest? There's no universal answer. Different people will weigh these factors differently. Some will say, absolutely yes, this is the future of our species, and we must push forward regardless of cost. Some will say, no, we should focus on problems here on Earth first, and space can wait. Most people are somewhere in between, recognizing value in both perspectives. Wanting to explore, but wanting to do it responsibly. Wanting to expand human capabilities, but not at the expense of human well-being. NASA's approach, historically, has been to pursue exploration while trying to manage risk to acceptable levels, not zero risk. That's impossible, but calculated risk, where the probability of catastrophic failure is low enough and the value of success is high enough that the mission is worth conducting. That calculation is different for every mission. For a satellite launch, the acceptable risk is fairly high. If it fails, we lose hardware and money, but no lives. For a crewed mission to low Earth orbit, the acceptable risk is lower. Lives are at stake. But the mission profile is relatively well understood. We've done it thousands of times. The unknowns are limited. For a deep space mission during solar maximum, the acceptable risk is higher again. Because the unknowns are greater. The exposure duration is longer. The environment is less forgiving. But we accept that higher risk because the mission enables future capabilities. Each Artemis mission builds on the previous one, teaching us more, expanding our envelope of safe operations, eventually enabling Mars missions. And Mars missions will enable the dream of becoming a multi-planetary species, a species that doesn't have all its eggs in one basket, that isn't vulnerable to extinction from a single planetary catastrophe, that continues to exist even if something happens to Earth. That's the long-term vision. And Artemis 2 is one step on that path. a step that requires Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen to accept risks that most people never face. To live for 8 days in an environment that could kill them if things go wrong. To trust in technology and training and teamwork. And to come back, hopefully, with data and experience that makes the next step safer. That's what's happening right now. Right this moment, while you're reading this, while you're going about your day. 4 people are out there, beyond Earth's protection, testing our limits, expanding our capabilities, risking their lives so that someday, maybe, humans can live beyond Earth. Not just visit, live permanently. And whether you think that's worth it or not, whether you care about space exploration or not, you have to acknowledge the courage it takes, the commitment, the sacrifice, not just from the crew, but from everyone involved, and from the families who watch and wait and hope. And what we're learning from Artemis 2 is genuinely important. This mission is the first real-world validation of deep space radiation management systems under solar maximum conditions with modern instrumentation. Let me put that in perspective. Every previous Apollo mission flew during solar minimum or relatively quiet periods. Apollo 8, the first crewed mission to orbit the Moon, launched in December 1968. Solar Cycle 20 was ramping up, but still relatively quiet. Apollo 11 through 17, the landing missions, all flew between 1969 and 1972. Still relatively quiet overall, despite the August 72 event happening between missions. We have models and simulations for what happens during active solar conditions. Computer codes that calculate particle transport through shielding. Biological dose models based on laboratory experiments. Statistical models of solar particle event, frequency, and intensity. But we've never tested them with actual humans in actual deep space during an actual active solar period. Until now. The data from this mission will be invaluable. The HERA sensors are measuring the real radiation environment in real time. Not a simulation. Not a model. Actual measurements of cosmic ray flux, of any solar particle events that occur, of how those particles interact with Orion's structure, of how the dose accumulates over time. The crew members are wearing personal dosimeters, measuring their individual exposure. When they return, their biological samples will be analyzed. Blood work to check for chromosome damage. Indicators of radiation exposure at the cellular level. This data will calibrate the models. Tell us where they're accurate and where they're not. Tell us whether our shielding estimates are conservative enough. Tell us whether the shelter protocol works as designed. And all of this matters enormously for future missions. Artemis 3 is scheduled for 2028. That mission will land on the lunar surface. The crew will spend several days there, exposed to the same radiation environment, but without even the minimal protection of spacecraft structure overhead. Just the habitat and spacesuits during surface excursions. If a solar particle event occurs while they're on the surface, they can't shelter in Orion. Orion will be in orbit. They'll have to shelter in the habitat. Or, if they're out on a traverse, in the rover. Or, if they're far from the habitat, in their spacesuits. The spacesuits provide almost no protection. Fabric and plastic. may be equivalent to a few millimeters of aluminum. Better than nothing, but not much. So if Artemis 3 faces an August 1972 level event during a surface excursion, the crew would be in serious danger. They'd need to get back to the habitat immediately, which might mean cutting short a geological traverse, abandoning samples, racing across the lunar terrain in the rover. Minutes matter, and on the Moon, you can't move fast. The terrain is rough. Boulders, craters, slopes. The rover maxes out at maybe 10 miles per hour, often slower. If you're 10 miles from the habitat when the alert comes, it takes you an hour to get back. An hour of accumulating dose in a spacesuit. An hour that could mean the difference between manageable exposure and radiation sickness. This is the operational reality of lunar surface missions. You have to plan traverses around the possibility of solar particle events. Keep excursions short. Stay close to the habitat, or accept higher risk for the sake of better science. Trade-offs. Always trade-offs. And then there's Artemis 4 and beyond. The Lunar Gateway. A small space station that will orbit the Moon, providing a staging point for surface missions, a place to store equipment, conduct experiments, and serve as a safe haven. The gateway will be in lunar orbit, outside Earth's magnetosphere, permanently. Crews will spend weeks there, maybe months. And Gateway won't have the same mass shielding that a planetary surface provides. It's a space station. Modules connected together. Thin walls. So the radiation exposure on Gateway will be higher than ISS. Much higher. And the crews will need robust solar particle event protocols, designated shelter areas, radiation monitors, real-time space weather forecasting, the ability to respond quickly when the sun erupts. All of this needs to be tested and validated. And Artemis 2 is the first step in that validation. But the bigger picture is Mars. Everything we're learning on Artemis is preparation for Mars. Because Mars missions will be fundamentally different from anything we've done before. The distance is enormous. Mars, at closest approach, is about 34 million miles from Earth. At farthest, it's about 250 million miles. Launch windows occur every 26 months when Earth and Mars are positioned favorably. And once you launch, you're committed. The trajectory is set. It takes about 7 months to get to Mars. Then you stay there for about a year and a half, waiting for the next favorable alignment. Then, another 7 months to return. Total mission duration, about 2.5 years. 900 days. Most of that in deep space. No magnetosphere. No atmosphere. Just the spacecraft and whatever shielding you can carry. The radiation dose from cosmic rays alone, accumulated over 900 days, is significant, approaching NASA's career exposure limits. But cosmic rays are the predictable part. The real concern is solar particle events. Over 900 days in deep space, the probability of experiencing at least one major solar particle event approaches certainty. Not 50%, not 70%, 90+%. You will face a solar particle event. Question is how severe, and whether you're ready. NASA's current Mars mission architectures include radiation shelters, a designated area of the spacecraft with extra shielding, water tanks, polyethylene, equipment arranged to maximize mass thickness. When a solar particle event is detected, the crew retreats to the shelter and stays there until it passes. Could be hours, could be days. During that time, the rest of the spacecraft is largely unoccupied. You can't do experiments, can't exercise freely, can't prepare meals in the galley. You're confined to a small shelter, waiting. This is not sustainable for a 900-day mission. If you have to shelter once a month, that's 30 times. 30 periods of days each where the crew is confined, unable to perform mission tasks, unable to maintain physical fitness. It becomes a psychological burden and a mission planning nightmare. How do you keep the crew healthy and productive when a significant fraction of the mission is spent huddled in a shelter? There are proposals for better solutions. Spacecraft designs with more mass, using water and waste as shielding, positioning propellant tanks to create protected zones, using lunar or asteroid material as bulk shielding, active shielding concepts that generate magnetic fields to deflect particles. All of these are being studied, but none have been demonstrated. None have been tested with actual humans in actual deep space. Artemis 2 is testing the baseline. Passive shielding, improvised shelter, real-time monitoring, 30-minute response window. This is the minimum viable system for deep space radiation protection. If this doesn't work, then more complex solutions are necessary. And we need to know now, before we commit to a Mars mission. Because the stakes are higher, the distances are greater, and the consequences of failure are more severe. If something goes catastrophically wrong on Artemis 2, the crew is days from Earth. If something goes catastrophically wrong on a Mars mission, the crew is months from Earth. And in some phases of the trajectory, rescue is physically impossible. You can't send another spacecraft to intercept them. The delta V requirements are too high. The timescales are too long. They're on their own, completely. This is the frontier of human capability. Not just technological capability, psychological capability. The ability to function effectively, knowing that for months at a time, you are farther from help than any human has ever been. That if something goes wrong, there's no cavalry coming. That you and your crewmates must solve the problem yourselves or die trying. Apollo crews face this for days. Artemis crews face this for days. Mars crews will face this for years. It's a different level of commitment, a different level of risk, and it requires a different kind of person. Not everyone can handle that. Not everyone should. But there are people who can. People who look at the risks and say, yes, I understand, and I'm going anyway. Because being part of humanity's expansion into the solar system is worth it. Because contributing to knowledge that will outlive you is worth it. Because doing something that matters is worth it. Reed Wiseman, Victor Glover, Christina Koch, Jeremy Hansen, they're those people. And they're out there right now, testing the systems that will enable Mars missions, testing the protocols that will protect future crews, testing whether we're actually ready for this. Right now, as I'm recording this, as you're watching this, the Artemis 2 crew is in interplanetary space. Active region 4405 is still on the solar disk, still active. The 10% daily probability is still accumulating. Other active regions are rotating into view. The coronal hole high-speed stream has arrived. The geomagnetic environment is disturbed, and the crew is out there, 200,000 miles from Earth and getting farther. On April 6th, they'll reach their closest approach to the Moon, about 4,000 miles from the lunar surface, or 6,400 kilometers. They'll swing around the far side, where Earth is completely blocked from view. Radio communication will be cut off. If a solar flare erupts during that time, mission control won't be able to warn them. The Hera sensors will be their only indication. Then they'll come back around, pick up the signal, and begin the long coast back to Earth. Splashdown is scheduled for April 10th. If they make it to April 10th without a major solar particle event, we'll have learned something important. That the system works. That the models were conservative enough. That we can manage solar maximum deep space missions. But let's be specific about what making it means. Because there are gradations of success and failure here. The ideal outcome is obvious. The crew completes the mission. No solar particle events occur. Radiation exposure stays within predicted nominal ranges. All systems function correctly. The lunar flyby produces excellent scientific data. Splashdown happens on schedule. The crew is healthy. And we validate everything. The spacecraft design, the radiation protection protocols, the forecasting systems, the operational procedures. Everything works as intended. Mission success. That's what everyone is hoping for. But there are other possible outcomes. Suppose a moderate solar particle event occurs. Not August 1972 level, but significant. X-class flare. Noticeable particle flux. The crew executes the shelter protocol, moves the equipment, configures the shelter, stays there for 12 hours while the event passes, accumulates some additional dose, but within acceptable limits, then resumes normal operations, completes the mission. That's still a success. In fact, in some ways, it's more valuable than the ideal case. Because we'd have real-world validation that the shelter protocol works. Not in simulation. Not in theory. In practice. With actual astronauts, actual solar particles, actual dose measurements. That data would be gold. It would tell us exactly how effective the shelter is, how well the crew can execute the protocol under stress, how accurate our forecasting is, whether the Hera sensors perform as expected in high-flux environments. All of that information feeds into future mission planning, makes Artemis 3 safer, makes Gateway safer, makes Mars missions more feasible. So a moderate event that the crew successfully weathers would actually be scientifically valuable. Not something to hope for. But, if it happens, not a disaster. Now, suppose a more severe event occurs. Larger than expected. The shelter provides protection, but the crew still accumulates significant dose, approaching or exceeding NASA's career limits. Not immediately dangerous. No acute radiation sickness. But enough to raise long-term cancer risk. The mission continues. The crew completes the lunar flyby, returns to Earth on schedule. But post-flight medical evaluations show elevated chromosomal damage. DNA strand breaks. Markers of radiation exposure, within survivable ranges, but higher than desired. That's a partial success. The crew survived. The mission objectives were met. But the radiation protection wasn't quite adequate for the conditions encountered. That tells us we need better shielding for future missions. Or we need to be more conservative about when we fly. Or we need better forecasting to avoid severe events. Valuable information. Hard won. At the cost of increased health risk to 4 people. Not a disaster, but not ideal. And then there are the failure scenarios. Suppose a severe solar particle event occurs and the shelter protocol fails. Either because the event is more intense than design limits, or because something goes wrong with execution. Equipment can't be moved quickly enough. A water container ruptures. The crew can't get to the shelter in time. Whatever the reason, they accumulate doses high enough to cause acute radiation sickness, nausea, vomiting, incapacitation. They can't perform mission tasks. Navigation, system monitoring, troubleshooting. The spacecraft is effectively uncrewed, even though 4 people are aboard. Mission control has to decide. Do we try to accelerate return to Earth? Burn extra propellant to shorten the trajectory? Risk a non-nominal re-entry to get the crew to medical care faster? Or do we stick with the planned trajectory and hope the crew recovers enough to function by re-entry day? Both options are risky. Both have potentially catastrophic failure modes. And mission control has to choose in real time, with incomplete information about the crew's actual condition. That's a mission failure, even if the crew eventually survives. Because we'd learn that our radiation protection is inadequate, that our assumptions were wrong, that we're not ready for this, and that would force a complete re-evaluation of the Artemis program. Maybe delay Artemis 3 by years while we redesign systems. Maybe put Gateway on hold. Maybe push Mars missions further into the future. Enormous consequences, beyond the 4 individuals directly affected. Because the implications ripple through the entire space exploration community. And then there's the worst case. The scenario nobody wants to think about, but everyone has to acknowledge is possible. A catastrophic solar particle event, beyond anything we've seen in the satellite era. Maybe not beyond August 1972. Maybe worse. The kind of event that occurs once a century, or once a millennium. Rare, but not impossible. The crew shelters. But it's not enough. Doses exceed lethal thresholds, and there's nothing mission control can do. They're 200,000 miles away, days from Earth, even on an accelerated return. No medical facilities in space. No way to perform bone marrow transplants or blood transfusions. Just watch, and wait, and hope. That's the nightmare scenario. The one that keeps people awake at night. Not because it's likely. It's not. The probability is very low. But it's not zero. And when you're responsible for crew safety, even very low probability catastrophic events matter. They have to be considered, planned for. Even though there's ultimately very little you can do if they occur. This is why NASA takes radiation risk so seriously, why they invest in forecasting, why they design shelter protocols, why they set conservative mission rules. Because the consequences of getting it wrong are unthinkable, not just losing a crew, though that would be tragedy enough, but potentially ending human deep space exploration for a generation. Because public support for space exploration is fragile. It's strong when missions succeed, when we land on the moon, when we send back stunning images, when astronauts wave from the International Space Station. But it's brittle. It cracks when disaster strikes. After the Challenger explosion in 1986, the shuttle program was grounded for nearly 3 years. After Columbia in 2003, another 2.5 years. Those were accidents, technical failures, things that could be fixed with better engineering. But a crew lost to radiation during a deep space mission? That's different. That's the environment being fundamentally more hostile than we anticipated. That's nature saying, "You're not ready." And the political response might be to pull back, to say, "This is too dangerous. We need to wait until we have better technology," which could mean decades, maybe longer. Maybe it ends crewed deep space exploration entirely, at least for our generation. So the stakes of Artemis 2 extend far beyond this one mission, beyond these 4 crew members. This mission is a test of whether humanity is ready to expand permanently beyond Earth orbit. And the answer we get over the next 7 days will shape space policy for years to come. If the mission succeeds, even with moderate challenges, it validates the approach. It says, "Yes, we can do this. Let's continue." Artemis 3 moves forward. Gateway proceeds. Mars planning continues. The momentum builds. If the mission encounters serious problems, even if the crew survives, it forces reassessment. It might slow things down, make us more cautious, require additional precautions. That's not necessarily bad. Caution is appropriate when lives are at stake, but it does delay the timeline. And in space exploration, timelines matter. Engineers retire. Institutional knowledge is lost. Political priorities shift. Budgets change. Momentum is precious. Hard to build. Easy to lose. So, every mission counts. Every success builds the case for the next mission. Every setback erodes support. This is the reality of publicly funded space exploration. You have to deliver results. You have to demonstrate value. You have to maintain public confidence. And you have to do it while taking real risks. Because without risk, there's no progress. But with too much risk, or with catastrophic failure, the program ends. It's a narrow path to walk, and NASA has been walking it for decades, generally successfully, with occasional stumbles, but always recovering, always moving forward. Artemis 2 is the next step on that path, a big step, bigger than Artemis 1, which was uncrewed, bigger than ISS missions, which stay in low Earth orbit, comparable to Apollo in terms of distance and exposure. But with modern technology, modern understanding, modern capabilities, and modern risks. Because the solar cycle doesn't care that we've improved our technology. The sun does what it does, and we either prepare adequately or we pay the price. Right now, the preparation seems adequate. The spacecraft is performing well. The crew is trained and capable. The systems are working. The forecasting is as good as it's ever been. But adequate means good enough for most scenarios. Not all scenarios. There's always the tail of the distribution, the rare event that exceeds your design basis. And when you're operating at the edge of human capability, in environments we're still learning to navigate, those tail events are real possibilities. Not just theoretical. We can't design for every possible contingency. We can't plan for every extreme. At some point, you have to accept that there are scenarios you can't survive. You just try to make those scenarios as rare as possible and hope you don't encounter them. That's where we are with Artemis 2. We've done everything we can. The crew is as prepared as they can be. The spacecraft is as robust as current technology allows. The support systems are in place. And now we wait and watch and hope that the sun cooperates. Because ultimately, that's what this comes down to. The sun. That massive ball of fusing hydrogen 93 million miles away. That has been shining for 4.6 billion years. That will continue shining for another 5 billion years. That doesn't know or care that 4 humans are currently in its line of fire. That just does what stars do. Fuses hydrogen into helium, generates magnetic fields, produces flares when those magnetic fields reconnect, accelerates particles, sends them streaming into space, following the laws of physics with no regard for human hopes or plans or dreams. We can't control the sun. We can only observe it, try to predict its behavior, and prepare to deal with the consequences. That's all we can do. That's all we've ever been able to do. And for 4.6 billion years, the sun has been doing its thing, creating solar wind, producing flares, generating the radiation environment that makes deep space dangerous. For 4.6 billion years, there were no humans to care. For most of that time, there was no life at all. Just physics. Just stars and planets and cosmic rays. Only in the last few million years did humans evolve. Only in the last few thousand years did we develop civilization. Only in the last century did we develop the technology to leave Earth's surface. And only in the last 50 years did we venture beyond Earth's protective magnetosphere. We're newcomers. Newcomers to a universe that existed long before us and will exist long after us. And we're trying to expand into that universe, trying to become a spacefaring species, trying to ensure our long-term survival by not keeping all our eggs in one basket. But the universe isn't hospitable. It's not designed for life. Life is an exception, a fragile exception that requires very specific conditions. Liquid water, atmosphere, magnetic field, moderate temperatures, stable star, protection from radiation. Earth provides all of that. It's a sanctuary, a rare oasis in a hostile cosmos. And when we leave Earth, we leave that sanctuary. We enter an environment that's fundamentally opposed to our existence. Vacuum instead of atmosphere. radiation instead of protection, extremes of temperature. No food, no water, no oxygen, unless we bring it ourselves. We survive out there only because of technology, because we're smart enough to build spacesuits and spacecraft, because we understand physics and can engineer solutions, because we're adaptable and creative and persistent. But technology has limits. Engineering has constraints. And sometimes, despite our best efforts, the universe wins. That's what makes exploration dangerous. And that's what makes it meaningful. Because easy things don't prove anything. Anyone can do the easy thing. The hard thing, the dangerous thing, that's what separates progress from stagnation. That's what drives us forward as a species. The willingness to attempt difficult things, to take risks for the sake of knowledge, to push beyond what's comfortable and safe, to say, we don't know if this will work, but we're going to try. Because Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen could have stayed home. They could have chosen safe careers, comfortable lives, no radiation risk, no possibility of catastrophic failure. But they didn't. They chose this, chose to climb into a spacecraft and let it throw them at the moon, chose to spend 8 days exposed to cosmic radiation and solar particle events, chose to be the test case for systems that have never been tested under these conditions, because they believe it matters, because they want to be part of the story of human expansion into space, because someone has to go first, and they're willing to be that someone. That's courage. That's commitment. That's the human spirit at its best. Not reckless, not suicidal, but willing to accept calculated risk for something larger than personal safety. For knowledge, for capability, for the future. And we, watching from Earth, comfortable and safe, we owe them recognition of that. We owe them respect. We owe them support. Whether this mission succeeds perfectly or encounters challenges, because they're out there doing something most of us will never do. Taking risks most of us will never take, for reasons that benefit all of us, even if we never leave Earth ourselves. Because the knowledge gained from Artemis 2 will advance human capabilities. The technology developed will have spin-off applications. The inspiration provided will motivate future generations. That's the value of space exploration. Not just the immediate scientific data, not just the engineering achievements, but the demonstration that humans can do hard things, that we can overcome challenges, that we can expand our presence beyond one planet, that we're not limited by our current circumstances. That's what Artemis 2 represents. And that's what's at stake over the next 7 days. And the sun doesn't know 4 people are out there. It doesn't know about shelter protocols or probability models or 53 years of waiting. It's simply a star. 93 million miles away, in peak activity phase, with magnetically complex regions aimed at the inner solar system, doing what stars do, following the laws of physics without regard for human plans or hopes or fears. So here's the question that the Artemis 2 mission is asking. Not the technical question of whether we can build spacecraft that survive deep space. We can. We've proven that. But the philosophical question of how much risk is acceptable for what only risk can purchase. Space exploration is fundamentally a negotiation between human ambition and the universe's indifference. We want to explore, to expand, to learn, to become a multi-planetary species. The universe doesn't care. It presents conditions. We adapt or we don't. We accept the risks or we stay home. Artemis 2 is us saying, we accept the risks. We're going. Not because it's safe. It's not safe. Not because the odds are zero. The odds are never zero. But because some things are worth the risk. Understanding our place in the cosmos. Learning how to live beyond Earth. Pushing the boundaries of human capability. Answering questions that can only be answered by going. And maybe, just maybe, proving that we're capable of more than we think. That humans can thrive in environments we weren't designed for. That we can manage risks that would paralyze us if we thought about them too carefully. That courage isn't the absence of fear, but the decision to act despite it. Over the next few days, the sun will either cooperate or it won't. Active region 4405 will either remain quiet or erupt. The probabilities will either favor us or they won't. And 4 people, Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen, will either return safely or face a crisis that tests everything we've built. We won't control the outcome. We can only watch, wait, and hope that the universe sends a favorable reply. But regardless of what happens, the fact that they're out there right now, beyond Earth's protection, during solar maximum, for the first time in over half a century, is itself an answer to a question humanity has been asking since we first looked up at the night sky. Can we do this? Can we really leave our planet and survive in the cosmic environment? The terrifying part of the Artemis launch that nobody is talking about isn't the rocket. It's not the spacecraft. It's not the technology. The terrifying part is that we're finally, actually, genuinely testing whether we can survive beyond Earth during the worst the sun can throw at us. And for the next 8 days, we're going to find out.